student participants from United Arab Emirates and China and Sri Lanka and Nepal. We wish to reach out. This institute has many foreign collaborations, and we are extremely keen to improve the foreign student, foreign faculty, and foreign collaboration component in our routine activities as much as possible. We also are very keen to realize the dream of the Prime Minister of this country, who raised the slogan, "Make in India." Normally one is used to hearing this phrase with the past participle form, "Made in India," but for a change, the Prime Minister wants things should be made in India, and that's why he appealed that come and make in India. In order to promote this philosophy, IIT Kanpur has started an event called Innovations in Manufacturing Practices. This is an event which is co-sponsored by Indian National Academy of Engineering, and this year we are happy to have Bharat Heavy Electricals Limited as one of the co-sponsors. The idea of this particular event is to promote an initiative, a mentality among the students to try out something innovative about manufacturing. There was a time, a few decades ago, where the contribution from manufacturing sector to the nation's overall GDP used to be over 40%. Today this is about 12.5%. In order to keep with the country's aspiration, we wish this contribution should soon go up to 20, even 25%. In order to realize this dream, we want to promote the culture of hands-on experience, try out, fail, and learn in the process, and create a manufacturing hub and base in this country. So I won't take any long. I would end saying that we are indeed grateful to each one of you who have come here to participate in various contests. We are particularly grateful to all the dignitaries here seated on the dais who have come, from who each one of them is not only a well-acclaimed person, but probably a pioneer by their own right in different disciplines. And we will all have the privilege of hearing to them either tonight or tomorrow. So don't miss that opportunity. I happen to see now that Dr. Radhakrishnan has just stepped in, and you are all aware that the way he walked in quietly, the same way he realized the dream for this country to participate in Mars mission, and India did it at a cost which not only is very competitive but is surprisingly low, and that was possible in this country through the very dedicated efforts of Indian Space Research Organization. So welcome, Dr. Radhakrishnan. I have a long speech. We are here only to say this particular event being inaugurated and open. So let us look forward to listening to all our dignitaries here, and I wish all of you will have a very pleasant stay and take home very pleasant memories of IIT Kanpur. Thank you very much.
Thank you so much, sir. I would now like to request our chief guest, Dr. Techkriti'15, co-inventor of fiber optics, to speak a few words.
Long, long ago, I sat in an audience as a student, an engineering student at Rutgers University in New Jersey, just like you're in this audience now. At that time, I was the first person in my family ever to go to college. So it was a pretty scary time for me because I wasn't really sure whether I was going to make it or not. But I did study hard and I did get through, and I ended up going on and getting a PhD. And from being a student sitting in the audience like you, I have to say I never dreamed that one day I would end up being a co-inventor of fiber optics, and that this would lead to a career through science, through engineering, later as a business executive, today as a retired executive, but as a director of several companies, and still actively involved doing consulting work in engineering and in fiber optics. I feel very, very fortunate that I went through that kind of a career, and that was because of the opportunity to be just like you out there studying engineering. So I encourage all of you to follow the path. I have a colleague with me this evening. His name is Kasyapa Balmarthi, and he is a graduate of engineering, electrical engineering here at IIT Kanpur in 1992. Stand up, please. Kasyapa and I work together as scientists in the area of fiber optics for a company called OFS Fitel. It's headquartered in the United States, and as I say, I'm a director of that company. But Kasyapa is here in India and is doing a lot of interesting work on developing and simulating next-generation fibers and systems that would be based on these fibers. And I'm going to put a little plug in now. Study hard, because we're looking for bright young people to come work with us at OFS. And if you're interested in that kind of a challenging technical career, that's the guy to get in touch with. So thank you again. I appreciate being here, and I look forward to the conference and talking to you more in the future. Thank you.
Thank you so much, sir. Now I would like to invite the guest of honor, Dr. Umakant Chaudhary, Executive Director, Research and Development, Bharat Heavy Electronics Limited, to come and address the audience.
Good evening, everybody. Professor Indra, Director, IIT Kanpur, dignitaries in the dais, all the invited guests, faculty members, and my dear students. It is a great opportunity for me today when I got a invitation to attend this function and to be the guest of honor. And of course, my visit was for signing a MOU with IIT Kanpur tomorrow. Just now Director told. We are working in various areas. By seeing this Techkriti'15, what Director was telling, he wants to take students towards the innovation, creativity. The moment we start thinking about the creativity and innovation, the term we say make in India or made in India, they are only possible. Today, when you want to have a collaboration with a foreign collaborator or any OEM, whether you say power plants, whether you say transportation system, or you say oil sectors, anywhere you want to go for a collaboration, today people are reluctant to give you the collaboration. Or they want to have a business sharing. They will not give you the documents. In India, the energy sector, if you see, initially we had the 250 megawatt sets. Subsequently, they were upgraded to 500 megawatt, 660 megawatt, 800 megawatt. It is going and increasing. It is because we want to cut down our carbon emissions. We want to have a higher efficiency. If you take subcritical sets or supercritical sets, or if I take a advanced to 8% higher efficiency or 10% higher efficiency. If we talk of a generator, the efficiency may be 99%. If a transformer, also similar efficiency I can get. When you talk of transmission, there is a lot of loss in transmission loss. But when you talk of a boiler and a turbine, the amount of coal you put inside, the power conversion which is done, the efficiency is very low. It is something like 35-36%. It can be increased to 45 and 46% if you go for high temperature operation or a high pressure operation. Something like we operate our sets maybe around 600 degrees centigrade and 265 atmosphere pressure. That is the steam temperature and pressure, which can be increased to 710 or 300 bar pressure, 300 atmosphere pressure. Then you can get a higher efficiency. So that can say that we can conserve our coal, we can enhance the efficiency of the total system. This is only possible when we are able to design ourselves the generators, we are able to design the high pressure, high temperature turbines, we are able to design our high temperature and high pressure boilers, and we are able to provide all the latest, I would say, instrumentation system, let it be fiber optic based or any other systems, so that we are able to control the power plant and we are able to achieve the maximum efficiency, or any time whether you say it's a full load operation or say part load operation, I'll be able to get a maximum efficiency. Anytime when you say it's a part load operation, a part load, definitely our efficiency and other factors are less. So we need to optimize our operations. That's why all this instrumentation, latest, the art of instrumentation is like going for fiber optics, transferring signals instead of transferring by through cables, which gives a lot of errors, and you don't get the signals properly. So definitely, just one of our dignitaries just now he was talking, that helps a lot. When you come to, this is what is, when you go for such a high temperature and pressure, the problem comes is, what is the material we use? Whether in India we have such material available? No. We have to import such material. And such a material, can I get a very large length forging? No. Then whenever I am operating at a high temperature, I use a high temperature grade forging. Whenever I am using a low temperature steam, I use a low time, and both I can join it by special welding process. So a lot of research has to go in when how these high temperature materials are going to behave when you are subjecting them to different temperature and pressure, or you make a design. So these are the challenges, and we have a consortium like BHEL, AJICA, NTPC working together with the guidance of India government to come out with such plans, so that India can have this technology without any collaborations. Because all the technology, whatever we have now, with certain supports we have been doing, whether it's a 800 megawatt or a 660 megawatt, but this is one of the technology which will be completely made in India, or I would say make in India. So when you go to transportation sectors, similar issues we get. It's like earlier days we had a system where we are using DC drives. Now slowly it is going to VFD fed AC drives. And this kind of a system, or tomorrow when you think of high-speed trains, or you think of magnetic levitation, which is already there in some of the countries. Maybe a lot of time is there for us to enter into such areas, but we need to do some work in these directions. When we talk of transmission, and let me say gas insulated switchgear, let us say 400 kV gas insulated switchgear, it was not available in India, we have to import. When we say make in India, that it has to be made, how much time we can depend on, we don't get a collaboration for such equipments. And BHEL has developed this 400 kV gas insulated switchgear. Now we are in a position to market it, give it to customer, which is totally indigenous design, and we are in the process of developing 765 and 800 kV such system. So which will make all these things, like everything is made in India or make in India, and all the technology will be available with Indian companies. And we are not depending on, suppose BHEL today doesn't make this gas insulated systems, any other company they can charge any money, because there is no competition. Similarly, if you make these generators, whatever BHEL is making, because of that price, definitely in the Indian market we are not paying more. Some of the cases definitely are being imported. With the global competitions, some of the Chinese and other when there is a breakdown, whether there will be support. Like VHL, the moment there is a breakdown, VHL sends their engineer by flight and get the system rectified and whole thing is immediately connected to grid. Such a support can we get from outside? So there is definitely a question mark. There are many new areas where we can think of creativity and innovation, and just I have given some examples, whether you say it's a nano, how to make a nano fiber, whether we can make it, and how to apply this nano fiber for aerospace industry, or whether you can use for transformers, you can use for electrical machines. This conductor, which has got a very good strength and it's a very lightweight. Suppose you say a Boeing, 50% of the wires weight can be reduced if the moment you go for carbon nanofiber based conductors. But there is a long way to go. How to grow these nanofibers? It is a thing VHL we have been working. Many of the IITs have been working in these nano centers. But second, it's not only we do the research, we have to see how this research is applied for the common man, and how this research can get us some business. That is what is there. That is what VHL is also looking to have a joint working with all the IITs, where VHL having an industry, know how the manufacturing process is known, and where the IIT, the analysis or the design or many of the basic research which can be done in IITs, when they come together, definitely we can say that many of such equipments or products which you can say it is a make in India, or we can make it, we can say it's made in India. Similarly, there are some new advanced areas like superconductivity, just now we are discussing. It is an area we have been working since, let's say, last 25 years or 30 years. Initially, the low temperature, many of the people may be working here. When it is a low temperature superconductor, niobium titanium or niobium tin, when you immerse in liquid helium, we get superconductivity. A wire which is carrying 5 amperes can carry around 500 amperes or 600 amperes. You can see how you can make the system compact. But how to circulate this helium liquid is very tough. Is it practical? Maybe a short sample I can make a magnet which is static, but if one go for a rotating application or even for a static applications, can you maintain it? So these kind of issues are there. Then subsequently now we have these high temperature superconductors, though they only store superconductivity at nitrogen temperature or helium, low temperature helium gas. So this is also one of the upcoming area where we can have many systems which can make the system very compact. We can say fault current limiters. If you say smart grid, what is the smart grid? Like that, we have to have some systems when there is a voltage collapse or there is a frequency change. We should store a lot of power which can be pumped back to the system in a very short time. How do you do that? If you have a superconducting magnetic energy storage system, such high energy can be stored and can be pumped back. Or if you say the load management system, that is also one of the area which is coming up. Suppose I know the phase angle or the voltage at all the places of all over the India and feed to a network, and you say how the power flow can be managed. Suppose there is a voltage collapse at some place, from one more point the power can flow. Such kind of studies definitely will help us to cut down our power outages, and definitely our country like India, where the growth is that the power demand is so high, and as the GDP is growing, and definitely it will grow at a faster rate, and definitely the industrial demand also will definitely come up in India, and many such requirements will be there, where you don't have to import all the many of the manufacturing equipments which are being imported. Now VHL is insisting that we should go for make in India. Such things can be made. But only thing is, as a student, you must have a dream. If you want, you have a dream, definitely you can achieve it. And like just to give an example, last year when this 30-year-old girl, she has climbed Mount Everest. Because she had a dream and she had the achievement motivation that could make her from a Telangana girl. She has the Prime Minister also congratulated. So I would say, let us hope that India will have a progress, and we will definitely focus on Make in India. VHL will focus on Make in India with the joint working with all the institutes. And I'm sorry to having taken a little more time. Wish you all the best, and wish all this Techkriti' a grand success. Thank you.
Professor Manna, Director IIT Kanpur, Chief Guest Professor Schultz, Guest of Honor Dr. Hilmer, Mr. Umakant Chaudhary, Professor Harold Rose, Professor Radhakrishna sitting among the audience. It's indeed a very proud moment, first of all, to welcome all of you to this event, which is now 20 years old. As told to you a little while ago, we began in 1995 as a very small kind of a festival, and over the years this festival has grown both in terms of magnitude as well as in terms of participation as well as in terms of finances. The jump in the amount of finances that we have been able to garner over the years is really appreciable, and a program which we started with a couple of lakhs now runs into multi-millions. This is a tribute to the marketing skills of our students. As I stand before you, I am reminded of my speech several years ago from this dais as the Dean of Student Affairs, and at that time I had charged the Techkriti team as well as all the teams of such festivals which are organized all over the world, that the amount of money that we gather and that we spend should be used wisely.
Welcome back, everyone. So, Dr. David Carl Hilmers is a former NASA astronaut with assignments including work on rocket upper stages as well as shuttle software verification at the Shuttle Avionics Integration Laboratory (SAIL). In addition, he was the astronaut office training coordinator, worked on various departments of defense payloads, served as a spacecraft communicator (TACCOM) at mission control, worked space station issues for the astronaut office, and served as head of the mission development branch within the astronaut office. His other spaceflight missions include STS-26 Discovery, the first flight to be flown after the Challenger incident, STS-36 Atlantis, STS-42 Discovery launched from the Kennedy Space Center, and many more. A veteran of 4 space flights, he has logged over 493 hours in space. So hear him speak his success story himself. Please put your hands together for Dr. David Hilmers.
Thank you very much for inviting me to come here. It's quite an honor to be speaking to students and faculty at one of the most prestigious universities, not only in India, but across the world. Tonight, I'd like to talk to you a little bit about my story. I think the introduction kind of gave my story up to maybe 20 years ago, and I'd like to maybe fill you in on a little bit that's happened since then. I grew up in a very small town in the Midwest, in the middle part of the United States, and the population of my town was probably less than what is in this audience tonight. I came from very humble beginnings, like perhaps many of you, yet I had dreams, and so tonight what I'd like to share with you are dreams, some of them fulfilled and some of them yet to be realized. And I'd like to leave you with several points. One is never, ever let anyone tell you that your dreams can't be achieved, that you may not have the money, the intelligence, the determination to make your dreams come true. That is false. Never let someone tell you that. Secondly, it's never too late to realize your dreams. I'm still finding that out now. And finally, with the great honor that you have to study here goes great responsibilities. You've been blessed with intelligence. Your presence here shows that. You've been blessed with skills. I challenge you to use those skills not to seek out prestige or honor for yourself or money or big salary, but rather to do those things that will make this world a better place to live. And I hope and pray that you will find that out early in life, and you'll find that your life is much more satisfying if you do so. So, if I can make the projector work. Somehow our slides aren't advancing. Can someone more technically oriented than myself help me with this? Okay, that arrow key. All right. So this is where I am now. This hospital is in Houston, Texas, where I'm serving as a professor in the medical school there, in the largest medical center in the world. And this hospital that I work at is a hospital, our charity hospital. It serves people from around the world that come to the United States. It serves people that have very little means, that have no means to pay. This is where I spent the last 2 weeks working 14 hours a day before I got on the airplane to come here, days and nights. And it helps achieve a part of one of the dreams that I had when I was a young man, and that was to go to places where there are no doctors. And over the last few years, I've had the opportunity to go to the Philippines, to Kenya, to Cambodia, to Haiti, to Central America, and most recently to Liberia during the Ebola epidemic. and here in Iraq during the war. Well, I grew up, as I was saying, in a small town in Iowa, a state where there's a lot of corn, a lot of pigs, not so many people. And I didn't ever think of myself one of my dreams was not ever to be an astronaut, but I went to school to college during the Vietnam War, and during that time, there was a lottery to find out who would be going into the service, and it was the only lottery in my life I've ever won. And I was drew one of the lucky numbers to go into the military, and I chose to go into the Marine Corps, the United States Marine Corps, and went on to get my wings in the late 60s and early 70s. This is me in my airplane. I served not only in the air wing of the United States Marine Corps, but also with the ground troops. And this is me with a forward air control team. And this is the airplane I flew, the A-6 Intruder. It was a all-weather attack airplane, and this one is in a museum now. They no longer fly; they're kind of dinosaurs, but it was a very worthy airplane. Later on, when I was in the Marines, I had my first opportunity to kind of live out my original dream of becoming a physician, but the Marine Corps lured me on to go to graduate school, and I got a doctorate in electrical engineering on the west coast of the United States. And this is my son. At the time, he was young, helping me with my books. And like many things in life, things don't change too much. He's now in his late 30s and still living with me. And that kind of led to being at the right place at the right time. Being an astronaut wasn't a dream of mine, although I thought that being in the space program was an incredible challenge and something that I thought was for other people, not for someone that grew up in a small town in Iowa. But the space shuttle program started about the time that I finished graduate school. And I was overseas serving as a commanding officer in a small unit in Japan when a message came across my desk that NASA was looking for astronauts for the space shuttle program. And up to that moment, I'll have to say that I had never really thought about becoming an astronaut, but I said, what the heck, I'll put in my application, and lo and behold, about a year later, they asked me to come and be one of the second class of shuttle astronauts, and this is me in the spacesuit. So, like anything else, whether it's being an engineer, a doctor, or whatever field, you just don't automatically become an astronaut the day that you arrive or they tell you you are one. There's a lot to learn about orbital mechanics, various types of sciences, how the shuttle works. And so it took about 4 years of doing work for other astronauts on their missions. I arrived in 1980, and the first space shuttle mission launched in April of 1981. I was selected for my first flight in 1984, and it was the first flight of the space shuttle Atlantis. Atlantis was a very space-worthy shuttle, and it flew for almost 30 years and now rests in retirement at the Kennedy Space Center. So if any of you have the opportunity to go there, you can see Atlantis that I flew for the first time. And this was a Department of Defense mission, and so that's me in my younger days with a mustache, the only Marine on that flight. And going into space for the first time is always going into the unknown. Someone can tell you what it's like, but it's impossible to really explain all the sights and sounds and feelings, sensations that you'll have. And so you're very anxious to have that first mission under your belt, but you're also somewhat anxious about how you'll perform. The worst thing for an astronaut is somehow messing up on their mission and having to come back and say that. So you're nervous about a lot of things, about your safety. Getting on a space shuttle that was built by the lowest bidder is always kind of interesting. Strapping on your back, your eyes to the sky, and just thinking about what's about to happen. As the engines, as the countdown clock counts down, about 6 seconds before the launch, there were two types of motors. There was a solid rocket motor. There were two of these, each of which had 2.5 million pounds of thrust. And then there were three liquid-fueled engines that had about 400,000 pounds of thrust apiece. And those were you could throttle these, and therefore we could start them about 6 seconds before the mission, test them out, and find out if they were working properly. And if they weren't, you could actually shut the mission down in the last couple seconds. And that actually happened on a couple of flights. So about 6 seconds before the mission was actually started, you would feel the thrust of the the liquid-fueled rockets gimbling, being tested. And then as they counted down to 5, 4, 3, 2, 1 at 0, the solid rocket launched and you were on your way. It was kind of a slow thrust, kind of like a kick in the seat of the pants, but nothing at all like launching off the deck of an aircraft carrier. It wasn't that kind of acceleration. But the sights and the sounds, the fire outside, particularly when you launched at night, and the vibration was something very very hard to describe. You gradually build up thrust, and you had what we call maximum dynamic pressure about 60 or 70 seconds into the mission. As you picked up speed and you interacted with the atmosphere, in about 2 minutes into the mission, you were 120,000 feet above the ground and about 100 miles downrange. At that time, the solid rocket boosters, the fuel had been expended. They separated from the vehicle. They went into the water and were reused for the next mission. Then you continued on for another 6.5 minutes on the thrust of the liquid-fueled engines. And this was more like being on electric motors. You were now above the atmosphere. The G-forces built up. They were longitudinal Gs, so they went through your chest rather than the radial type G that you would get when you were flying a fighter airplane or something, where all the G-forces go down through the long axis of your body. And so it would feel like something heavy was sitting on your chest, and it would become difficult to talk, difficult to breathe. Finally, at 8 minutes and 32 seconds, you'd reach a speed of 17,500 miles an hour. So you went from 0 to 17,500 miles an hour in about 8.5 minutes, and went through a lot of territory during that time, and it was quite a ride. Suddenly then you would be weightless, and everything floated, and that was quite a transition. I like to, one of the best things about being on orbit is to take a look at the Earth from space. And this is over the Himalayas. This is Mount Everest right in the middle of the picture. I can't tell a whole lot about that mission because it was classified, but I'll have to say that if you go to Wikipedia, you might be able to see a few details about it. I won't say if it's true or not, but I can say that there's a lot of speculation about what we did on that one. So I came back from that mission, was already assigned to another flight, and the flight that I was assigned to was going to launch a satellite that would ultimately go around the poles of Jupiter and explore the poles of the sun, and in a kind of a slingshot maneuver. It was going to be called at that time the Solar Polar mission, which ended up not launching on the space shuttle because of the fatal accident of the Challenger in January of 1985. NASA had to go back to the drawing boards, find out what went wrong with that flight, why it crashed, and what to do to make future shuttle missions safer. I was fortunate enough to be chosen for the next crew. So I was on the first mission after the Challenger accident, and this is the patch from that mission. We had a sunrise to mean the new beginning, and the 7 stars of the Big Dipper represented the 7 friends of ours that died on that mission. There are many, many changes that we made to the space shuttle program as a result of the Challenger accident. One of them was, for the first time, we started wearing these very well-known spacesuits called the launch and entry suits. It turns out that the Challenger crew probably was alive until the time that they hit the water, and if they would just have had a way of jumping out, parachuting out of the cabin, that they might have survived. And as a result, after we found that out, we went from just wearing a basic flight suit with a life preserver and no parachute to these special suits that would provide pressurization and oxygen for about 45 minutes in case of some sort of launch failure. They had thick lining so that you had an exposure suit. If you went down in the northern Atlantic during the wintertime, that you would be able to survive for some period of time. They also had G-suits built in so you would be able to survive the re-entry process. And also they had a parachute that was on the back. All in all this equipment weighed about 100 pounds, so it was quite heavy, it was quite hot, but at least it gave us some semblance of an opportunity to survive an accident. Of course, once you get into orbit and everything floats, one of the problems we discovered was that you have to somehow corral all these suits that you've just gotten out of, because you don't wear them the whole mission, you just wear them for the launch and entry part. This is a picture that I dug out of my files, looking over India, looking out over the Himalaya plateau and mountains. The Ganges is running down through here. So a nice panorama, what it looks like from space as you look out the horizon, rather than looking straight down like we did in that previous photo of Mount Everest. This is a picture of what it looks like when you're re-entering. This is the inside of the cockpit. These are the computer screens. Interestingly, we talk about memory in terms of gigabytes. What we had in the shuttle computers that flew on our missions, we had 128K of memory, and that held enough memory for us to run all the flight software. The missions that landed on the moon only had about 64K of memory. So, you can do a lot if you're a clever programmer with a little bit of memory. So these are the computer screens that drive help you interface with the computers. The keyboards are here, very large pads, so that you could punch the keys with your gloves on. And you might be able to see the resolution is not real good here, but as you look on this computer screen, we're re-entering, and you see various lines here, and these are the trajectories that you need to stay between. If you flew too steep a trajectory, in other words, the shuttle was flying below this line, you would come in too steep and you would burn up, you would exceed the thermal limitations of the shuttle tiles. If you came up too high, not steep enough, you would just basically skip out into orbit and have to try again. So it was very important to fly the shuttle down these lines. Most of it was done by computer, of course. The other thing to notice here is looking out, this is plasma being built up, very hot plasma that's built up outside the shuttle, up to about 3,000 degrees centigrade. And of course there were special tiles based on the heat characteristics that would be felt by the shuttle as it re-entered. But as you looked out, it just looked like fire that was surrounding the shuttle as you re-entered. And this is coming back home, landing at the Edwards Air Force Base on that mission. And this is President Bush meeting us at the bottom of the shuttle. My third mission was in 1990, and this was a mission for the CIA, and so I can't again tell you a whole lot about this other than I'd lost my mustache by that time, and this is we flew again on Atlantis. My second mission was on Discovery, and we were an all-military crew. And because of the launch trajectory that we took, we went further north and south over the world than any other human beings have ever been in space. We flew a higher inclination, that means latitude, farther north and south than anyone has ever done, and probably will do, just because it doesn't, usually you don't need to fly that far north and south. But it was a great mission as far as taking pictures. This is one of the film cameras. Back in those days, we still were just developing the first digital cameras, so all our cameras at that time were film. This is Antarctica from space. The next two slides show you what it looks like in New York City. This is Long Island, Manhattan. This is where the Twin Towers were at that time in 1990. And then the same picture at night with a different, that was with a 5-inch camera. This is with a 35-millimeter camera, but New York City at night. This is what many of the great cities around the world look like at night. This is a picture of the Aurora Borealis, which, as many of you know, is a result of particles from the solar wind spiraling down the Earth's magnetic fields and interacting with oxygen and nitrogen in the atmosphere, giving off photons of green and blue light. About this time, I was thinking that what I really want to do with my life, and I had decided that I had nearly 20 years in the military at that time, and also had 3 flights with the space program, and I kind of thought that was for me enough, and what I wanted to do was go off and go to medical school. And so I told NASA that I thought I was thinking about retiring. I was going to stay on while I finished my prerequisites for medical school, and they said, okay, that's fine. And then unfortunately, one of my friends was killed in a plane crash, and he was due to fly on a mission that was coming up in a few months. And so NASA came back to me and said, we need someone experienced to step in and fill in for your friend and be on that crew. And I said, well, I'm about to take the entrance exams in a week for medical school, and I've been taking these classes. And they said, well, that's fine, you can do both. And so for the next 9 months, I finished my university prerequisites for medical school, took my exam, and trained for a mission that had 70 different experiments on. So it's just kind of to tell you, if you are really determined to do something, that you can find time to have, even if you're extremely busy, which I was at that time. And this was called the International Microgravity Lab number 1, IML1. So we had, on this particular mission, the shuttle was configured with a tunnel between the front part, which is where you fly the vehicle and where you eat and sleep, to the back where there was a laboratory in the cargo bay. And this housed about 70 different experiments, ranging from physics experiments to biomedical, engineering experiments, a lot of basic science. We had mosquitoes and rats on board, and all sorts of other types of experiments. We grew wheat. So it was a fun experiment from a science standpoint. It was the first mission that I was really kind of a scientist. This was our crew. determine what the action of the inner ear and the semicircular canals with the balance organs, how it operated in space in comparison with how it operated on Earth. We also grew crystals of gallium arsenide, which were at that time were used in very high-speed computer applications. This is a picture looking at the horizon of the Middle East. At the bottom of the screen, you see the delta of the Nile River, the Red Sea, the Sinai Peninsula. Here's the Dead Sea. Israel's along. This is the orientation that we would usually fly the shuttle in. It was the most heat, thermally, the best environment for the shuttle to have the tiles up towards the sun. So we usually flew upside down. So if you look out the overhead window, you were looking straight down at the Earth. And that was my last mission. This was the sunset, kind of a sunset to my career. And my last landing, this one was also at the Edwards Air Force Base in California. But throughout that time, I still had this dream of being a doctor someday. And even when we didn't have a doctor on board, I always volunteered to be the physician. dreams, but yours is just starting. And you're going to be the ones that have the opportunity to find out what's out there. You have the intelligence and the skill and the time to learn answers to many of the questions that have eluded us. And once again, I would just tell you to devote yourself to the betterment of humanity with the skills that you have to make and leave this world a better place. So thank you very much for listening to me. Okay, so do you want to have them speak first and then have questions later? I'm sorry? Okay, so let's start this one.
Thank you so much, Dr. Hilmers. And the people, I hope that you all have many questions, but you can get them sorted out. Dr. Hilmers is here for another day. So we'll be starting with the talk of Dr. K. Radhakrishnan in a few minutes. So please stay seated. Thank you so much.
Hello everyone. It has been a new and complex mission. The journey has begun. The challenging phase is yet to come. These were the words of Dr. K. Radhakrishnan after the success of India's Mangalyaan mission. Dr. Radhakrishnan is an Indian scientist and was the chairman of the Indian Space Research Organization, ISRO, between 2009 and 2014. It was under his leadership that India's Mangalyaan successfully settled into the Mars orbit, making the country the first and the only nation to have done so on its maiden attempt. The recent launch of the heaviest and tallest GSLV Mark III, the successful re-entry of the unmanned crew module, success with the space flight of an Indian cryogenic engine and states, and Chandrayaan-1 were his other landmark achievements. Owing to these achievements, Dr. K. Radhakrishnan is among the 2014 top 10 scientists chosen by the prestigious journal Nature and also a Padma Vibhushan awardee. With a vision so bright and success paving his way, Dr. K. Radhakrishnan has rightfully made a place in the pages of India's success stories. Please put your hands together for Dr. K. Radhakrishnan.
Thank you. Thank you very much. How many of you would like to join ISRO? Raise the hand. Wonderful. Distinguished Director of the Institute and my beloved friend, Professor Indranil Manna, all the distinguished invitees who are present here, faculty members and all the friends who are present here. It's a great privilege for me to be again talking from this stage. And as some of you may recall, in June 2014, I was here. That was a convocation address. Probably one of the best convocation events I have seen. And on that day, your director told me 3 students want to meet you. And they ensured that I come here and talk to you at 10 o'clock, which is probably the first time I am giving a talk at this time. But what I wanted to convey to you is there are some people to whom you cannot say no. And the more you deal with them, you get more closer to them. You get respect for them. And I should say, Arpit Kabra, who has been interacting with me over the last few months, especially over the last 3 months, and we had almost 25 emails exchanged, several telephonic talks. I found I was talking to a matured CEO of an organization, and that is the greatness of Kanpur IIT, and the credit goes to your family members, your teachers and your professors who have groomed you to take such kind of position. And certainly you are going to be success in your life, in your career. That is guaranteed. I was asked to speak about the recent strides in Indian space missions. Just they were listed out. Mars Orbiter mission. Cryogenics technology development, and how did we get into a successful flight in the year 2014. What we did for GSLV Mark III, the unmanned crew module, the different satellites that are in the orbit providing service to the humanity. So these are the things which I am going to speak. But I would like more of interaction rather than my giving the speech. This is a wonderful picture, and let me start from where Dr. Hilmer stopped his talk. I was fortunate during the last 4 to 5 years to interact closely with one of his colleagues, Charles Bolden, who is now the administrator of NASA, of working together in international fora, interacting on joint programs, and currently India and United States, ISRO and NASA are working towards building a satellite together to be launched in the year 2019-20 for helping the humanity, not only the people of the respective countries, and to look at issues like whether we can predict earthquake. This is something which, if we can do, it will be a great service for humanity. We also worked together recently in the Mars Orbiter mission, where the deep space network of NASA was fruitfully used for supporting the Indian Deep Space Station. And the experience, that learning that they had in several missions to Mars, failures and successes, were all there at the back of my mind, back of our minds, back of the mind of the entire ISRO team, when we got prepared for this complex mission of finally putting a satellite into the orbit of Mars. So let me thank him for the exciting talk and thank his colleagues for the kind of fraternity that we have developed over the several decades in the area of space. And today we are finding synergy and how together we can do a lot more in this switch. If you look at the story of the Indian Mars Orbiter mission, one thing which I learned after September 24th is there is no need to tell any Indian about the Mars program. You go to a school, you go to a college, you go for a function, you go for a social function, they will tell you what Mars Orbiter mission is about. They will tell you India was the first country to achieve it, the first attempt. They will tell you the statistics of success and failure. And some of them will also tell you why those missions failed and what we learned out of it. So this is something India gained over the last 4 years in the field of space. And on September 24th, in the schools of India, the students came at 7 o'clock in the morning, assembled there in the auditorium, and saw the whole operation. And we got heaps of postcards, rolls of paper and clothes on which they had written down, "Congratulations, all the best, we are proud of you." And this is another transformation that we saw on that day. And if you look at the Indians who are in other parts of this world, they are really excited about it. They feel proud that they are Indian. And finally, if you ask a student today what you want to be, what you want to choose as a career, science and technology, aerospace engineering, these are all the words that will come on the top. That is what we have achieved. And if you recall 4 years ago or 5 years ago, people were discussing in the country, why are we spending 450 crores of Indian rupees for this kind of a mission where everyone has failed? Why are we attempting that? Can't we use it for something else for the humanity? But what we have shown over the last 4 to 5 years is, if you are clear about your objective, if you are clear about that path that you need to take, and if you are ready to go with grit and determination and not swayed away by the criticisms that come, but get the signals out of those criticisms and use it positively. If you can not only look at the overall strategy, but also get into the nitty-gritty of the details and get prepared for the failure modes and get ready, then nothing is impossible. That this is what the young people of ISRO as a team achieved. And when I say young people of ISRO achieved this, the average age of the Mars mission team was just below 30. And in ISRO today we have something like 4,500 people who have joined us after the year 1999. And what we needed to do as a senior management was to bring them all together to say that we are going to take up a mission to Mars. It is not going to be just a flyby, which will give you a few seconds of observational time, but a decent satellite to be orbited with the capabilities that we have. And what is that capability? We have a PSLV, which is a reliable 4-stage rocket. We have a deep space station that was built for our Chandrayaan-1. And we do have some experience in taking a spacecraft beyond the Earth's orbit, going up to 4 lakh kilometers. We have done an exercise and we were able to capture that lunar orbit positively. As compared to the 4 lakh kilometer, here we are talking about 55 million kilometer to 400 million kilometer. It's a long journey. And associated problems of communication delay. The need for providing autonomy in the spacecraft. And the kind of environment that was just talked about, the spacecraft has to pass through. The radiation environment it has to manage. The communication capabilities in terms of signal strength, the receiver sensitivity, all have to be managed. And very complex mission. That is on one side. That is for the engineers. But if you look at the voyage of nearly 660 million kilometers in a heliocentric orbit from Earth to Mars, one has to estimate the influence of Sun and all other planets on this body and ensure that on that day when we arrive in the proximity of Mars, we are at 500 kilometers plus minus 50 after a voyage of 660 million kilometers. And that has to be estimated when we start the voyage on December 1st. And unless that direction in which we are putting the spacecraft is correct, we are never going to reach anywhere near Mars. And if we are not able to estimate this precisely, we are not going to get the orbit that we are intending to. And if that propulsion system overperforms or underperforms, we will not get this right trajectory. And finally, if we have to reduce the velocity at that point near Mars, the propulsion system which was sleeping for 300 days has to be restarted and it has to give the predicted performance. So these were the challenges we had to meet. And what was the time available? August 2010, we said we are going to do it. In June 2011, we wrote on the paper saying that we can do it. And we convinced everybody in the country, ISRO, India is going to take a new direction in this area. And they supported us. And we had to use that opportunity that was available, the next opportunity, which comes once in 26 months. That is November 2013, we have to be ready with the satellite to be launched from Earth orbit. And then on December 1st, we have to start the voyage. Just compare. We compared with NASA. NASA had a mission, MAVEN. After all that experience that they had gained, they said we will have a number of instruments on this spacecraft, go very close to Mars, something like 150 kilometers by 6,000 kilometers, and they study they had. They had a rocket which had almost 10 times more power compared to our PSLV. And we ventured into this mission, but we did it. What we did for that is the one which I'm just going to tell you in a few minutes from now. This is our PSLV which I mentioned. The advantage that PSLV provided to us, apart from being a reliable rocket, is that it has 4 stages. And for the minimum energy transfer from Earth's orbit to Mars orbit, we needed certain conditions at the injection. And the PSLV, because of its configuration, was able to give us that point. Specifically, the argument of perigee of nearly 270 degrees, which even a slightly more powerful rocket like GSLV would not have been able to provide. But PSLV had that ability. But the difficulty for us was we had to design a totally different mission as compared to what we were doing in the past. In 20 minutes, this PSLV normally used to put a spacecraft into the orbit, but here we had to get that right argument of perigee. It was a 47 minutes flight. Logistically, we had to fire the last stage when the rocket is up in the South Pacific Ocean area. And we had to have specific design for each lift-off time, but we were ready with it to be loaded on the onboard computer based on the lift-off. So that was one aspect that we managed at that time. But the most important point was to realize a spacecraft within about 15 months without compromising on any testing. How did we do it? This is by 24/7. All the people, all were enthused, young people like you, enough energy, lot of ideas. They all assembled together and made that, because that day it had to be ready, and we did it. If you look at the reaction from the global community, I should say nobody believed that India will be able to do this mission. And if you look at the various blogs that they talk about, this was very clear. But the day the spacecraft was ready for launch, they said India is serious about it. But the day we started our movement along with MAVEN towards Mars, that is the first week of December, people took us very seriously. Yes, India is in the game. But as far as we were concerned, the people who were managing the mission, we were looking at all possible modes of failure where all it can go wrong. And we were keeping vigil. Probably this is one mission. For 300 days, the country was with us. Not only we were looking at this spacecraft. As somebody wrote, it is the most pampered spacecraft, because throughout we were looking at its health and its position. And all that was done. And on 24th, we did that job that you all saw. And today, the Mars Orbiter spacecraft is doing its job, intended job. It's almost completed 6 months now, and it is going to give us service for some more time. How much, that we will see soon. But we went through several learning in this process, which will give the country capability to put a larger spacecraft with a major scientific objective into the vicinity of Mars, and probably later do several kind of studies in synergy with other spacefaring nations. This is just to show the complex part. Engineers were on one side building spacecraft and rockets, but the mathematicians for the first time became the people in the front line for this mission. And we were all looking at the judgments, assessment, calculation about the spacecraft position and the future path that it need to take. When we were doing this Mars mission, there were a lot of criticism. Instead of working on this GSLV, which has been failing and failing and failing, why are they concentrating on this Mars? Some people said publicity. But the point is, we were working parallelly with that. April 2010, we had the first flight of the cryogenic engine and stage. And that we did after about 20 years of work. And why we had to develop a cryogenic engine? That is the first question. In PSLV, we did not use a cryogenic engine. All the power is provided by the solid rockets or the earth-soluble liquid systems. But if you have to put larger spacecraft, heavier spacecrafts into larger or bigger orbits, you require more energy. If you ask your colleagues from aerospace engineering, they will talk about specific energy. So if you have to put communication satellites which are of 2-ton, 3-ton, 4-ton class, you require heavy vehicles. And there we required the cryogenic engine technology. And in the world, there were only very few countries who had this capability. And our initial strategy was we will get the technology from outside. And for geopolitical reasons, we could not do that. But in 1992, India took a decision, we are going to do it. Again, another decision taken with grit and determination. We are going to do it, and once that is done, then it will be done. This is what we have shown. But we had to set up a number of facilities for this, and we were for the first time getting into this technology for a rocket. And we went through that phase. And in August 2010, when we had the first experiment, it did not work. And the next 3 years was a difficult phase for us, actually. Because we wanted to find out, with 800 milliseconds of data available from that stage, what went wrong. This itself was a great challenge for us. All possible failure scenarios were looked at. And there we talk about the fishbone diagram. All possible routes in which we worked out and attacked each one of those issues. We redesigned. We created new test facilities. And we tested this engine in the simulated high altitude condition. And during this phase, we could locate the culprit, what could have really given the problem, and we confirmed that issue. And then we went to the launch pad for this mission. Another story that I will tell you later. But what we did at that time on January first week was a very precise mission. And the GSLV, which had a jinx of nearly 4 failures, even without the Indian cryo, and this cryo failure all got through, and that was a landmark in the rocket technology development in India, giving us not only evidence that in India we can do a high technology engineering project. This was the message that this cryogenic technology gave to the country and other organizations in the country. If you look at recent one, GSLV Mark III. The GSLV, what I talked about so far, can put a 2-ton class communication satellite. But in communication, the scenario is changing. We go for high power, heavier communication satellites. Today, when we talk about GSAT-10, GSAT-8, GSAT-16, we get them launched from outside, mostly from French Guiana. Now this vehicle is going to give us that capability to launch our own satellites and also launch some of the foreign satellites. Today only our PSLV is used for launching foreign satellites. PSLV. GSLV is coming up. So this is going to be, in another 2 years, a rocket that can take heavier Indian and foreign satellites. What we did in December was an interesting thing. If you look at the history of launch vehicle development, SLV-3, first SLV-3 failed. ASLV, first and second ASLVs failed. We learned several things out of it. We learned for the first time through ASLV failure what is dynamic pressure. You ask aerospace engineers, they will tell you, as the vehicle accelerates, velocity goes up, and the atmosphere, of course it is becoming denser, but there is a point where there is a maximum, which is going to give problem for the structure of the vehicle. And ASLV broke down into pieces at that time. PSLV, first flight, was a failure. 3 possible failure scenarios occurred together. If all the 3 did not occur, we would have had probably a successful satellite injection. But all 3 happened, including some silly failure in the software. But that gave us a robust PSLE, which we are now saying 27 flights have gone successfully well. GSLV-2, the first one was an abort mission. So when we got into this GSLV-MR3, rightfully the question is, what are the new things that you have to understand, especially when there is a configuration which is totally different in terms of the L/D ratio, and as control engineer says, the mu alpha, aerodynamic instability, we had to test this during the atmospheric phase of the flight. There are several scenarios in which this can fail, and we looked at all those scenarios and we wanted to ensure that up to 120 kilometers, the rocket is robust enough to go, and that's what we did. So today when the cryogenic stage goes on the top of it, we have a foolproof vehicle available for carrying a satellite. And on the other side, the engine tests are going well for realizing this GSLV. So in a nutshell, the launch capability of India is going to go from the reliable PSLV, which can put a 1 to 1.5 ton satellite, to the GSLV, which is already available, and to the GSLV-MR3, which is going to come up in another 2 years' time. Here there is an astronaut who has gone and seen the whole, probably, world as we talk about. But what India has made now is the first step, the baby step for getting into the human space flight. A few years ago, right, in 2006-2007 period, we conducted studies and we found it is right for India now to get into human space flight, which is the logical next step in the space exploration. The need and the desirability of this was established, and we found India cannot afford not to do a human space flight in the near future. The point is, there are several technologies that India needed to learn for getting into the human space flight. Most of which we talked about. You need a reliable launch vehicle for a manned mission. And we talk about reliabilities of 0.99, one failure in 100 only can be tolerated so that the astronaut is safe. As the vehicle goes up, if there are any problems likely to happen for the launch vehicle, how do you save the astronauts? You require a crew escape system for that, like the aircraft has got a seat ejection system. So a crew escape system which will take you to a safer place, and it has to have higher reliability, better reliability. And they talk about 0.998, 2 out of 1,000 that needed to be developed. He talked about the space suit. In any eventuality, wherever he lands up in the Earth, whether it in sea or a jungle or any other place, the astronaut has to survive. So you need to have a space suit which is capable of providing that facility. Then, when you take a human being into this crew module, you require the environment in which the human being has to be there. The life support system. And when we talk about a few days, 7 days, we talk about an open loop system, means you just collect all that is coming out. But if it is for longer duration, it has to be recycled. It's a closed loop system that has to be developed. You need to monitor the health of this astronaut. So a lot of sensors, standards, testing, all that have to go through. And finally, as we come down for the re-entry, what happens? That need to be tackled. And what we did in this flight is to look at exactly the re-entry problem. We know the shape, you know the size, you know the velocity. As it comes down, we can calculate the thermal flux. We can model it, we can simulate it, but only in the actual flight we can make the measurements. And that's what we did in this flight. And here we are clear. As far as the landing is concerned, how we can manage a mission to come down, splash down in a given place, that was seen. So what we did is, as I said, the baby step into a possible human flight for the future. It's a new direction. Like we talk about the Mangalyaan today, I'm sure when you are there in ISRO, you'll be talking about the human going to an orbit around Earth and possibly then get ready for farther and farther places, including probably a voyage to Mars, which of course requires a very, very long time. I was very happy to be with the students of this institute when you made that small satellite. When they were building the satellite, there was a phase in which we had to tell them that by tomorrow, if the satellite is not ready, we are not going to put it in this mission. The wonderful thing, a few students in Bangalore and the rest of the students here in Kanpur worked overnight and they resolved a problem, and the next day the satellite was ready. When the students make the satellite, generally most of the support systems, including the separation system, all were provided by ISRO. But here there was a team that had innovative ideas in making such systems. So this is what really we want the youngsters to wet their hands, the faculty members to support them, the institute to develop facilities in which aerospace, satellite technology can be done in the institute itself. So this is one of the examples that we can talk about. But when you say we build a satellite for remote sensing or for science or for communication, there are so many technologies which come into the picture. And what distinguishes a space technology? It's a large system. Any student of system engineering should learn first how to look at the interfaces that take place between each one of them. If a control engineer does not know propulsion, if he does not know the structural dynamics, then he will not be able to design a control system for a satellite or a rocket. That is where you see the interdependence of disciplines coming into the picture. And the first learning here is it is interdisciplinary activity and they should know. So when I said in a mission control, large number of people are working, each one of them should know for any action that is taking place in one of the subsystems, what are all the implications there. And for the September 24th event to become successful, we had looked at all possible scenarios of failure and we sat down with 200 people who are participating in that mission and sat for 7 days on what can go wrong at that time on September 24th and how we are prepared. And everyone should know what is to be done by each and every person. So that is the beauty of this rocket. And that is the reason in space we say between chairman and the youngest engineer there is no difference as far as technical scientific matters are concerned, because this rocket or this satellite obeys the rule of mathematics, physics, chemistry and not the administrative orders given by people who say we are senior, we have more experience. So this is where the power of the youth, the inventive power of the youth, the energy of the youth, that needs to be unleashed. And then we can get several things. And then what we elderly people need to provide is the wisdom, not to condition them, but to tell them. This is what I heard when the vote of thanks was given and I was talking to the director. All these youngsters have a lot of energy, lot of ideas, new ways of looking at things. We should not constrain the new generation with what we think is right, but make them decide for themselves what is right for them. So this is what we do in our exercise, and that is one of the reasons why ISRO, people say, is a successful organization. This is the fleet of satellites that India has today. 25 satellites. Some are at 36,000 kilometer orbit doing communication, broadcasting, etc. A few of them going around the earth from pole to pole at about 600, 700 kilometer looking at the resources. And a few of them doing the navigation. IRNSS. The point is, these are like patients in the intensive care unit. They have to work for 10 to 15 years. There are rotating parts. If you look at a momentum wheel or a reaction wheel, over lubrication is a problem, under lubrication is a problem. If you look at the electronic components, whatever testing you do on the ground, there could be failures happening there. And a solar flare and such space environment, the space weather also changes the state of many systems there. So, constant vigil on all these systems are essential on one side. And since it is going to be used for the normal working of us, whether it is an ATM, whether it is a TV, whether it is a search and rescue system, the user finally gets affected. And how do we manage them in the orbit and also the operations on the ground? This is another complex activity which we deal with. And finally, why Indian program is unique? It is unique because not we do Mangalyaan or Chandrayaan or such kind of exciting, exotic things, but finally about 90% of our effort goes for serving the people. Looking at how the governance in the country, how the development in the country can be improved, how the farmer or the fisherman can get a better information so that they don't waste their energy, they don't waste their money, and there will be an improvement in the quality of life. Finally, this is the test of it. And where do we stand in this area in the world? I talked about it last time when I came for the convocation. First 6 groups, if you look at in this area, India is there. USA, Russia, European Space Agency, Japan, China, India. Then comes Canada, Brazil, etc., etc. Qualitatively and quantitatively, these have been evaluated by institutions, and one I should say, Futron in USA, which used 50 parameters to look at 15 organizations and evaluate it, and they have done it right from 2006, and India is there in the first 6. If you look at the quantitative parameters, there is a study by Japanese Science and Technology Institute, and we are there. We may not get the mark for the human space flight where others will get it. But there are several areas India is well above 6. Mars mission, we all say first attempt, we were the first one to orbit it successfully. If you look at the applications, we say we are the role model for the whole world on how it can be provided to all the people. From writing a paper on a new technique, to make it into a practical activity, to spread it across, to put it as part of the value chain of that farmer or the decision maker. This is what India has shown. Indian PSLV is sought after, and 40 satellites from other countries, 19 countries we have launched. GSLV is now getting market. These are one class of launch vehicles. India has built 2 communication satellites on commercial basis for European customers. And Indian's remote sensing constellation is supposed to be one of the best, and nearly 20 ground stations all over the world have been and are receiving data from these remote sensing satellites. Chandrayaan enabled a major discovery, and today we are at Mars orbiter. And in the year 2015, India is going to launch a multi-wavelength observatory in space called AstroSat. And the astronomy people in the world say that for the next 5 years, AstroSat is going to be a very major resource on which the global community is going to do research. So this is what India is providing. It provides challenge. It provides a unique environment for all to work. And it is one of those unique organizations. Why it is unique? It's a subject of study. Many people are now studying actually, not only from India, from abroad. So this is the kind of organization we are. And I have been asked to also speak about a few words about what we are going to do in the future. Essentially, we are going to talk about space exploration and the space technology and space up. But there are a few things which I did not talk about. One, of course, is the space. When we have 25 satellites doing the work like part and parcel of everybody's life, we need to worry about security of that. This is something which we are worrying about. One is the debris management, and we are getting in a major way. The space security, this is another major area. Space robotics, and this is one temple of robotic technology, and I'm sure that the space robots made by you would find place in the future in Moon and in Mars. And when we talk about human habitat in Mars after 20, 30, 40 years, this is one area where we need to do a lot of work. Human space flight plus space robotics. This is the key word, because it is easy to send a robot, but robot will do what it is programmed to do. It is difficult to send a human being and bring back safely, but he or she has cognitive capability. So we need to have a unique mix of this human in loop and the space robotics. This is what we are trying to do. We study Moon, we study Mars. There is a need to understand Sun, and we want to do that by putting a satellite in a peculiar point. It is called the Sun-Earth Lagrangian point 1, which is 1.5 million kilometers away, and then study the corona aspects of Sun. This is going on. That mission is the mission. Navigation. Operationally, you know GPS system, you know about the GLONASS, you know about the Galileo which is coming up, you know the Chinese system. But India is developing its own regional navigation system for India and areas around India. We have already 3 in the orbit which are working well, and the 4th one is going to be launched on 28th of March at around 5:20 p.m. the lift is. With that 4 satellites, we will be able to determine the position, and what we expect is an accuracy of 10 meters in the position, and this is going to give us strategic capability that is a new direction. Apart from providing the Gaggan facility, the satellite-based space-based augmentation of GPS for an accuracy of 2 to 3 meters for aircraft navigation, both onboard as well as landing. That is already available today, but this is going to be our own navigation system. So this is the broad areas in which we are getting into. Some time has been kept for question and answers. I am sure that a few questions we could take.
Thank you so much, sir, for such an inspiring and informative session. We would now like to invite questions from the audience.
Yeah, there is.
Sir, may I ask you, what is the source of your inspiration? What inspires you so much to do so many wonderful things?
That inspiration evolved. The story is, I was also like you, an electrical engineering student. And at that time, one is not very clear about the career direction. First target is to get a good job. On the same day, I had to appear for an interview in the Space Science and Technology Center, which is today's VSSC, Tumba. On the same day, I also had to go for an interview in IBM. At that time, it was a big employer in the country. So I went to my professor who knew me very well, what I know. Then he suggested to me get into Tumba. They are developing satellite launch vehicle. So that is the starting point. There was another milestone in my career after doing my MBA in 1976. I could have gone to a corporate world, but I decided I will work in ISRO. Why I went back to ISRO? For several reasons are there. And one reason, it provided me a platform for doing several things actually. If you want to do, sky is the limit. But as I progressed, as I got into space application, I found this is one place where it makes a difference. A fisherman in the sea coast, he goes to the sea and looks at the board, he is saying that I go there and I get fish. That is coming from the information provided by the satellite. If you look at a person who is locating a well for groundwater, where he takes a lakh of rupees from the bank, if he doesn't find water there, he gets into a problem. Sometimes it can be a suicide also. But if you are able to provide an additional information from the spatial dimension, and he is able to get a better result there, it is a great contribution. So I found in this process there is something we can do to the people around you. Apart from doing all this great technology, finally he respects you. One day I telephoned a doctor. He asked me, where are you working? I said, I'm in Incois. You are doing something for fishermen, is it not? It's a great thing to listen from somebody like that. So that is where their purpose in life. Finally, whether you are doing high-end research, whether you are writing good papers, it has to have a relevance at some point of time to the society around you. So this should be your motto. I'm not saying that all others are not important. They are all important, they are required for this system. But finally, keep a word how it is going to be used for the people. Ask this question to yours. That's all.
Thank you, sir. Thank you very much.
Hello, sir.
Okay.
So my question is that is ISRO looking forward for any outer space mission, deep space missions, like going for? We are mostly hearing about people going for only Mars or for Moon. Are we going to explore Uranus, Neptune, or other outer solar system planets?
At the moment, our priorities are Moon, Mars, and study sun. A point which is 1.5 million kilometers. Yes, there are studies on asteroids, as the former speaker talked about. The world is looking at asteroids. There are several reasons for it. There is also danger. There was a study, an asteroid called Apophis was predicted to be coming to the geostationary orbit of Earth in 2029 as per one estimate. Of course, that estimate is changing. But the point is, there are things to be understood and studied, and this can be done together. So ISRO is also interacting with NASA in that area, what we can do in the area of asteroids.
Thank you. Hello. First of all, congratulations to you, sir, for the Mars orbiter mission success. And my question is, like, I'm from aerospace engineering background here in IIT Kanpur, and as you feel like young people from across country should come and contribute to your ISRO, but since our door is closed to get into ISRO, I mean, I don't understand, sir. Even though you study aerospace engineer, but our door is closed, we cannot contribute into ISRO. Like,
door is not closed, but there are people coming from another door. That's all the difference. See, ISRO started the institute at Trivandrum at a point of time when we were not getting people from these disciplines. So it was essential for the program to have at least 150 young people in avionics, aerospace, and physical sciences. Currently, ISRO takes about 300 youngsters every year. 50% from that institute, 50% from other places. Then when we talk about space, all disciplines are important in space. And in future, in Indian space program, it's into a major thrust area. So there is enough scope, and I am sure that door is not closed for you.
thank you, sir.
Good evening, sir. Sir, this is.
Yeah.
Good evening, sir. Sir, my question to you is, what is your view on a space station made by India? Like we have the International Space Station outside, and it is collaborated with almost a lot of countries. So why is India not a part of it, or is India looking forward to make a space station in the future?
See, the space station as it evolved has India was part of the manufacturers or owners of the space station. Number two, space station's life, how long it will go, was also uncertain, but now it is very clear it is going to go for 2020 plus. There are opportunities available for conducting several kinds of experiments using space station. On that, ISRO is engaged. And our interest there is to look at Earth observation system, Earth system science basically, not for using it.
Greetings, sir. Sir, I am quite at the start of my career as a first year in electrical engineering, and I don't want to make it sound like some career counseling advice, but I would like to know what options do I have as a research engineer in ISRO later in my career.
I'm an electrical engineer.
Okay.
Basically.
No, but I think times have changed, so.
No. Electrical engineering is same, whatever you say. It has not changed. But what happens is, basically I want to make one. We study in this 4 or 5 years in this engineering institute is only making us capable of learning more and more. And when we say I'm an electrical engineer, we learn mathematics, physics, chemistry, several other branches of engineering, plus a few more papers we study on electrical engineering. If you look at the ISRO people, many people who are in the senior positions, they have moved from one discipline to another discipline. And there cannot be a better example than what we saw just now, an electrical engineer getting into medicine. It is possible. In ISRO, I will give you one small example. One of my who is now the president of the Indian National Academy of Engineering. Your director works with him in the council. His MTech is in machine tool design from IIT Chennai. He became the person who developed the hydraulic control system for the first SLV-3. He is the person who finally designed the navigation guidance control system for our ASLV, PSLV, GSLV. You see the transformation taking place. He became the director of Vikram Sarabhai Space Center. For any rocket that goes up today, he is the final person to clear it, saying that yes, everything has been seen through and that goes. So every day. And I can look at mechanical engineers transforming this way, mechanical engineers getting into software, several things are happening there. Right? So these are not watertight compartments. That is one thing we have to understand.
Thank you, sir.
Should I start? A very good evening, sir. Sir?
Yeah.
Sir, a very good
evening.
Oh,
here. Okay.
Yes. Sir, I wanted to ask about space debris mitigation program that has been launched by the ISRO. Considering the fact that, sir, space debris has become a very huge menace as far as low Earth orbit is concerned, and various countries, including various foreign countries, have been developing their programs into high Earth and medium Earth orbits. So what are the various developments that have been made by the ISRO, and what are the various programs that have been launched by the ISRO in order to remove the space debris in low Earth orbit, or to launch the satellites in high Earth or medium Earth orbits?
From the quality of question, it is very clear you know the subject. Now, about 16,000 objects of various sizes have been catalogued in two things. In the satellites which are in the low Earth orbits, what are the probabilities of them getting into hitting? As the rocket goes up, what are all the problems going to happen in the path? There are 2-3 basic elements. One, need to have the observational capability. Today that capability is in USA with an NORAD. They provide that information. Second one is on the modeling part of it. Once you know the position, the rest of the analysis can be done. The third part, which is the most complex part of it, is instead of reacting, can we do the scavenging part of it? Research is going on that area. Now, looking at the Indian capability, we are excellent in modeling part of it today. We are developing capability for observation. There is a multi-object tracking radar which is coming up in Sriharikota, which is going to be commissioned soon, which can look at the objects which are in our 1,000-kilometer orbit, where our remote sensing satellites are going to be there. The next one is a research which is going on. And lastly, guidelines are getting evolved by the international body on you should not destroy, how to handle the nuclear devices which go in the satellites, etc. That's also parallelly going.
Hello, sir. Actually, I want to ask, what are the critical and sophisticated technology ISRO is looking after for human spaceflight missions?
See, as I explained in the beginning, one is to improve the reliability of the rocket that we are going to. It requires improvements in the design, avoiding the single point failures, providing extra margins and systems for understanding the health and finding out a potential disaster well in advance. This is one thing. Second one is the crew escape system. These are rockets which have to move the crew module at a higher acceleration to a safer place. The environmental control system provides a lot of opportunity for research in terms of the sensors, systems, etc. These are all to be done. And finally, of course, the astronaut has to be trained. That is another major aspect of it.
So,
re-entry, the thermal flux calculations, mission management, communication, whether you want to be in contact with the craft throughout, what percentage, globally how do you have the ground stations geared up for this purpose. These are all the new areas to be got into.
And what about the emergency escape system?
There is a crew escape system which I was talking about. In the ascent phase, if the rocket is going to fail, at least a few seconds in advance, if you are able to find out, then you can operate the crew escape system, which are again a set of motors which have to be fired and take the gentleman to or the lady to another area with the parachute system, etc., etc. We are testing those systems at the moment.
Okay, sir. The crew vehicle, whether it is in water splashdown or it will be in ground.
See, America has the land, but as far as India is concerned, problem. Assume that you require a large area. It has to be a precise landing. For any reason, you have to have an emergency landing in another place, and the control flight becomes a ballistic flight, you will end up somewhere else. So what we are looking in the initial flight is to have the landing in sea, either in Arabian Sea or in the Bay of Bengal. You need large tract of land where such things can happen and very precise landing. One day we may achieve that. Like space shuttle is landing today. But if it is a ballistic phase, may go somewhere else.
I'm sorry to say, but because of the shortage of time, this would be the last question.
Sir, today is the world of fighter planes, and DRDO is working on that. But in future 2050, there is the world of scramjets, which is which have a speed of 24 Mach and above. Is ISRO working on that?
ISRO is working on it. We call it air-breathing propulsion. A difficult area working. People say in the poetic words, lighting a candle in a hurricane. That is the kind of problem. What we have done at the moment is to have a small module operated on a sounding rocket, because that sounding rocket provides certain simulated conditions, and we are studying our ability to start ignition in that condition. But it's a long way to go as far as we are concerned. We have to obey the command of our MC.
Thank you so much, sir.
Thank you.
With this, we would like to wrap up the talk. There was supposed to be
Now how many want to join ISRO? More or less. Thank you, thank you. Door is not closed.
Thank you, sir.
Thank you.
A big round of applause for Dr. Hilmertz as well. A technical show on face mapping was supposed to take place, but because of the time delay, we are unable to show the exhibition. So it will be available in the Tech Planet for all 3 days. So anyone interested can have a look over there. Thank you so much.